Do you like that? I would swear you in Spanish right now. Habla español, diablo.
That was good. That was right. That was it. Okay. Oh, and we're still recording, but I muted that. All right. Second derivative test. Okay. Right. You will forget this. But I'll write it down. The second derivative test has nothing to do with inflection points, which is confusing right now because our second derivative, the only thing we've used it for is inflection points. And we use the second derivative, even in the language, to test for concavity, which is a bad word to use because then you like, oh, test for concavity, second derivative test, inflection points, okay? The second derivative tests, what does it do? It finds maxes in minimums. I'm really selling it here. In a less intuitive way than the more obvious first derivative test. That is a really good description of the second derivative test. I think I've tried teaching the second derivative test, just teaching it well, reinforcing it, and over again, students will be like, second derivative test, I have no idea what that is. It must be inflection points, right? What does it do? So I'm now making fun of the second derivative test in hopes that it helps you remember it better. Because the second derivative test finds the max or a min of a graph, but in a way that you already have the first derivative test, which works awesome and is really visual. And like, oh, I found my first derivative of 0. It goes up and then it goes down. Oh, it's a maximum. It's so intuitive, the first derivative test, that you'd be like, why would I want to learn a second derivative test? When would it be useful? And truthfully, it's only useful when mathematicians make specific questions to see if you know the second derivative test. So and it's going to happen. So we're going to have to know the second derivative test. It finds maximums and minimums also needing two things. So here's a review. The first derivative test was basically, one, you found f prime of x to be equal to 0 at some point. I'll call it x1. You made your number line and put x1, and then if you're like, ooh, it went from increasing to decreasing, those two things, right? This was the second thing, that made it a max. You needed to show two things that made it a max. The second derivative test says the following. Second derivative test. You still do the first part. You go, ooh, I found out f prime is equal to 0. And even though it would be very natural to do the first derivative test next, I'm going to skip it. And instead, I'm going to put a little x1 here again. Instead, I am going to plug in x1 into my second derivative and find out what happens. For example, you plug it in and you get a number. We're going to, don't like equals something. You can write something. but I'm gonna pretend that I got 3. We don't know what we'll get when we plug in a number, but let's pretend we got 3. If my second derivative is positive, I'm happy, things are concave up. And this, combined with this, says the only place I can be concave up and have my first derivative flat is a minimum. And so it's another way of finding a minimum. But it's not as intuitive because you're naturally always going to do this and your number line next when you're graphing. Because in our steps for graphing, we did the black, that's our preliminary. We did the green, and I'm really nervous. Did I forget to switch to purple? I think I did in the last question. I'm sorry. It's like 5 hours of learning lost on that last question. I got so excited about the cusp, forgot to switch to purple. I can see that I forgot. Oh no, did I? I did switch to purple. You guys are okay. Okay, you can take spring break off. It's gonna be okay. It's like everything was going well in math this morning until the moment we forgot to switch to purple, and my whole spring break plans got ruined. I had to relearn all of calculus from the beginning. So this is the second derivative test. We still find the first derivative equal to 0, and then we either find out if it's positive and concave up. Well, again, draw a little diagram here. It's really easy to see. These are the two things that you found when you find concave up and a first derivative of 0, meaning it's flat. The only thing that can happen is a minimum. And same thing, you can draw a little diagram. If you find out concave down, and you know that the tangent has a slope of 0, the only thing that can happen is a maximum. So the second derivative test isn't hard to understand. Thinking of those two reasons should make sense that it's a maximum or a minimum, but the name of the second derivative test makes you think of inflection points. It has nothing to do with inflection points. You already have a good first derivative test that you will always, if you're graphing, you will always use the first derivative test because it's in the natural flow of what you do when you're graphing. So you will never use the second derivative test unless you're given a question that specifically says that. Or they take little pieces of information, not giving you the whole picture, and say, hey, what can you tell me about this if I tell you this and this? And you're like, oh, you're testing to see if I know my second derivative test. So we are going to just use the second derivative test for this. And we're going to make a very big, oh, but it wants us to sketch. Oh, okay, we are going to save, I'm going to save you guys some time. Because it doesn't make sense to do the second derivative test and sketch at the same time. Because then if you were sketching, you'd accidentally do the first derivative test first anyways, and then you'd be like, oh, well, why should I do the second derivative test? So, let's take out sketch. You guys have sketched enough, and I'm going to make you graph tomorrow. So, oh yeah, now you're not coming? Yeah, okay, so using the second derivative test only. What would this look like? Well, we would find our first derivative just like normal. We wouldn't do any preliminary stuff, so I go right to green. First derivative test. First derivative, sorry. 3x squared minus 12. Set it equal to 0. Factor out the 3. Notice a difference of squares. And then do not do the number line for the first derivative. Instead, skip right away to your second derivative and find out the following, that the second derivative is just 6x. Okay, and now we'll make a couple of statements. At x equals -2, f prime of -2 is equal to 0. That is reason number one for both the first derivative test and the second derivative test. And reason number two, f double prime at -2 happens to equal -12, which is negative, which is concave down. And so we would know that -2 comma, and if we plugged in -2 back into the original equation, we would get 21, give or take 50, allow for mental math errors. -2 comma 21 is a max. There's your second derivative test. Why do we know it's a max? Here are the two reasons. One, it's equal to 0, and two, it's concave down. At x equals 2, we would have the same first reason, that f prime of 2 is equal to 0. And secondly, f double prime of 2 is positive 12, which means it's concave up, and that tells us that 2 comma, again, 8 minus 24, -11, give or take. It really, like, if we get the coordinates wrong, you're not going to care, but we'll hope that hopefully the mental math is right. This, by the second derivative test, is a minimum. And the reason I took out sketch is because if you were sketching, I would expect you to do the first derivative to find out where it's increasing and decreasing. You do that number line, and you would have done the first derivative test before you even got to the second derivative, and you'd be like, well, why should I do the second derivative test now? So this is the second derivative test. If you're just wanting to find max or min, some might argue this is pretty quick. Is it quicker than doing the number line? I'm not sure. Probably pretty similar, depending on the equation. So the second derivative test is not hard to do. It's not longer, but if you're just doing it, you're skipping some of the graphing steps that you would naturally do. So it feels a little contrived, because you would normally go, oh, when we're pre-calculus and calculus students, we kind of like systems. You didn't make it this far in logical classes by going, oh, I like to do things all over the place everywhere. I don't know why I keep getting math questions wrong. You're pretty sequential and you like steps. So something like this feels like we're cheating ourselves, like, oh, we should do the extra steps. But what it is showing us is that sometimes if we have different pieces of information, we know more about the graph than we think, even if we've skipped certain things. So sometimes things like this are helpful if you're working backwards or you were just given pieces of information in the middle, okay? What can you derive from that, or what can you figure out from that? Okay. Yeah, so this one doesn't have the second derivative test. We've done lots of sketching. Do you want to do this one on your own? Let's see, what do we got coming up? Oh, then we go into graphs. Yeah, that's more fun. Let's skip the sketching one. You can try that one on your own. Here, I'll go to the completed ones and there. Oh, but color coding wrong. Sorry. Take a picture. Get to zoom in 15 times. But it's on the video, so if you wanted to try it on your own, right, you could. And I explicitly wrote out in this one the first derivative test and the second derivative test. So again, showing the two reasons for, oh, I have to add. I even made mistakes in my first derivative test. And sometimes it's easy to make that mistake in that first derivative test because you're like, but I showed it was equal to 0 in my work above. I just didn't explicitly say it. It's important that we explicitly say the two reasons for the first derivative test so that we don't have issues like a non-permissible value that could come up. Okay. Now, to make your brain go somewhere else. Now we're just going to be thinking theoretically about graphs and the derivatives and the second derivative and working in both directions, but not given an equation. On yours, have I taken out this equation on your notes?
No.
Oh, I think I meant to. Okay. Well, so you have the equation. Sometimes you won't, and you'll just be given a graph. And that's coming up, well, I kept equations on both. And sometimes I won't give you the numbers. Okay? So if you had just this information that we have right here, what we know about this is we can draw both our number line for our first derivative and off to the side our number line for our second derivative. And so this is us saying, can we connect what we know about the final graph to what happened in the steps if we were graphing? Okay? So basically, what we're trying to do here is we have the graph, and we're working backwards almost to what the equation was and what was happening with that equation. So if I have the graph, can you tell that, oh, I have a maximum at -1? Which number line, the green one or the purple one, did that show up on? That showed up on the green one, right? That would be a stationary point. That would show up at -1 on there. What did the green line tell us? It told us where the graph was increasing and decreasing. We can see that that was a maximum. This would be increasing. This would be decreasing. And because of that, we know that on our derivative is positive here, negative here, and 0 at -1. For our second derivative, what are the points that we put on here? If there are any inflection points. Does our graph ever change from concave up to concave down? No. So what do we know? There would be no points along here. And it's always concave down. If it's always concave down, then our second derivative is always negative. I need to sketch the graph of f prime and f double prime. On f prime, I know that at -1, it's going to be 0. To the left of -1, it needs to be positive. Interesting. So I don't think drawing that straight line the way that we did is like you might go, oh, but I'm increasing here. Shouldn't my tangent also, like, because this is increasing, students want to make this increase as well, okay? But an increasing graph tells us the derivative is positive, and if your graph is positive, it's above the y-axis. If your graph is negative, it's below. Okay? Now, a couple of things that you could do with an equation like this that are good cheating methods, we'll call it. Maybe you look at the graph and say, I know it's a parabola. I know it's a negative parabola. If I have a negative parabola and I do the derivative, I will get a line with a negative slope. So that makes sense that the green line that I drew is a straight line and that it's going down because it has a negative slope. Right? Yes.
Why is f of -1 equal to 0?
So why is f of -1 equal to 0? Because on our original graph we have a maximum, so if I drew a tangent there, so anytime you have a graph, all of your maximums and minimums will always be stationary points, right? Will be critical points on this number line. And if they're critical points on that number line, that's where f prime of x was equal to 0. So it's going down. Now our second derivative. Our second derivative is always negative. Okay? Again, using a little bit of a cheating method of our first derivative, you would say, oh, if our first derivative was a -2x, maybe plus something or minus something. If I take the derivative of that, I'm just going to get a -2. So my purple graph is always negative and would look like this. But really what we're doing is we're using our number lines off to the side to draw something. And we're using a little bit of intuition of saying, if I have a parabola and I take the derivative, I'll get a line. If I take the derivative of a line, I'll just get a number. So a number will be a horizontal line. And the idea of these kind of questions is to give you a graph without an equation, without any scale. The answers would still be the same, right? Same, more or less. Okay, let's look at the second one. This time, this graph is the derivative graph. Again, off to the side, I'm going to draw my number lines to see what I know of them. And because the numbers are there, we'll use the numbers. But again, it could be that you didn't have any numbers whatsoever. On the green one, this time, what numbers will go on here? How do we see them from our graph? So we have to have a really good understanding It's like, okay, the numbers that I put on my number line for f prime are always where f prime is equal to 0. On my first graph, that happened to be at a maximum because I would think to myself, the tangent is 0. But this is the derivative graph. So if this is the derivative graph, it's telling me that here at -3 and here at 1, it's equal to 0. My derivative graph tells me that between -3 and 1, all my y values are positive. So I know they're positive here. I know that they're negative here and negative here. That tells me something about my original graph. My original graph needs to go down, then up, then down. What about my second derivative number line? Okay. My second derivative usually tells me inflection points of my original graph, but I do not have my original graph. I just have my derivative graph. So in this situation, we have to sort of think of, if this is the derivative graph, the second derivative graph is just the first derivative graph of the first derivative. That makes sense. So I could, in the same ideas that I did in the first example, I could say, I know that the one number that I'm going to put on here has to deal with this point at -1. Because the tangent of this would be 0, which means if I move from my first derivative down to my second derivative, it would be 0 on my second derivative. Right? And looking at my derivative graph, I notice that my derivative graph goes up and then down. Goes up to -1, then down. So what would that mean? That would mean this section is positive, this section is negative. And now I can take that and translate it back to my original graph and say, oh, so that means my original graph has to be concave up. And my original graph here has to be concave down. So the one single graph tells us a lot of information. Okay? So now we can graph the original graph. I will do the original graph in black. Technically, I'm going to draw over this one, just so that we keep our color coding thoughts the same. In green, because that matches up with my green number line, that is my derivative graph. My original one now in black, what do I know? I know that I need to have a minimum at -3, a maximum at 1, an inflection point at -1. And this is a little bit bothersome for some students, because you can basically put your minimum, maximum, and inflection point anywhere. So you're like, oh, minimum at -3, I want it here. Inflection point at -1, I want it here. Maximum at 1, I want it there. And then I need this concave up and this concave down, full marks. Someone else looks at somebody else's and like, your maximums and minimums are at different points. That's okay. Why is it okay? Well, if you were working backwards, okay, from an x² graph, if the derivative was an x² graph and you moved up, does it make sense that your original equation would be some sort of x³ graph? Okay? In fact, in this case, we could actually probably figure it out because we know what the equation is. But in your original x³ graph, can you see that there could have been a +7 at the end, And when you take the derivative of a plus 7, it goes away. It could have been a plus 17 at the end, and when you took the derivative, it would go away. If you think back to transformations in grade 12, what happens when you add or subtract numbers on the end of a graph? It moves it up and down. So this derivative graph is the same derivative graph for a whole bunch of x cubed graphs moved up and down. Doesn't matter where they are. When you take the derivative of that last number, it goes away. It's like it doesn't matter anymore. So that's why I'm allowed to make my maxes, mins, and inflection point sort of wherever. And then our second derivative, if I graph that as well, well, this has we know that -1 is where it's equal to 0, and it is positive on this side and negative on this side. It's the same graph that we drew for our derivative on the last one. It would look like this. I think the color coding is important, because otherwise things can get very confusing as we're going. All right, so there is some practice questions there. We're going to do that for the rest of class today.